So students, here we will see the isthmus and cut vertex. Definition: an edge E of a graph G is called an isthmus. Isthmus, that is also known as a bridge or cut edge. Bridge or cut edge if the number of components of in G minus E, number of components in G minus E is more than that in G. More than that in G. That is, if G is an edge of G such that G minus E is disconnected graph. Such that G minus E is disconnected graph. For example, suppose I have this graph . Suppose this is G and suppose here the edge E is given to us. Okay, and here let me draw suppose this is G minus E. So here G minus E is disconnected because of whom? This E. So here after deletion of an edge E, G becomes disconnected, hence E is an isthmus. Here note, after deletion of edge E from G, G is disconnected. G is disconnected. This says the edge E is an isthmus. Or bridge or cut edge. Bridge or cut edge. Another definition, that is of cut vertex. A vertex V in a graph G is called a cut vertex if the number of components in G minus V is more than that in G. That is, if U is a vertex in G such that U is vertex in G such that G minus U is disconnected graph. G minus U is disconnected graph. Then U is a cut vertex. U is cut vertex. Example for cut vertex. Suppose I have the graph. Suppose I will take it as such. Suppose this is a graph. Suppose this is the vertex V. This is G. Now here I will delete that V. So obviously the edges are deleted. This is G minus V. So G minus this V. So here this V the vertex V is cut vertex of G as G minus V is disconnected. G minus V is disconnected. Now let's write one note. Let GVE be any graph the edge E of a graph G, edge E of a graph G is an isthmus, if and only if E does not belong to any circuit in G. If it doesn't belong to any circuit in G, then it will be an isthmus. Now the next definition is that of connectivity. Connectivity. So first one, let G be a connected graph. Connected graph. The minimum number of vertices whose removal from G results in a disconnected or trivial graph. Trivial means what? A single vertex graph. There is no edge. A trivial graph is called the vertex connectivity. Vertex connectivity of G. Vertex connectivity of G. The vertex connectivity of G is denoted by K of G. K of G. Okay. Here note 1. If K of G equal to 1, then G has a vertex V such that G minus V is not connected. And V is what? V is a cut vertex. Number of cut vertices is nothing but the vertex connectivity. Another note is that if G is a complete graph, the complete graph with n vertices then K of G is what? N minus 1. Third, the vertex connectivity of Cn, that is what? Cycle graph with n vertices. N vertices is what? 2. The vertex connectivity for this is what? 2 for n greater equal 4 obviously. Fourth, if a graph G has a bridge, then the vertex connectivity of G is what? 1. That is K of G is how much? 1. For example, now here now there is a bridge, right? Then vertex connectivity is 1. So here this vertex simply it will be cut vertex. So here if we eliminate that, then the K of G is how much? 1. So this is G1, this is V, therefore K of G1 is what? 1. But if we take this graph, suppose this is G2. So in G2, the relation of any single vertex doesn't result a disconnected graph. However, after deleting 2 vertices, if 2 vertices are deleted, then it will give us a disconnected graph. Therefore, here K of G2 is how much? 2. 2 vertices are deleted, then we get a disconnected graph here. Okay. Now, the next one, edge connectivity. So, definition. Let G be a connected graph. G be a connected graph. The edge connectivity of G is the minimum number of edges whose removal from G results in a disconnected or a trivial graph. The edge connectivity, number of isthmus or number of bridges, that is nothing but the edge connectivity, right? Edge connectivity. The edge connectivity of G is denoted by lambda of G. Now let's write few notes. Note 1. If G is a disconnected graph, then edge connectivity is what? 0. Second, if G is connected graph and G has a bridge, then edge connectivity of G is how much? 1. For example, here these two edges gives us a bridge. So here I can say lambda of G1 is what? That is the edge connectivity of G1 is how much? 2. Again, what about this? So here it will be G2, suppose, with 5 vertices and these edges. So here whenever we eliminate 3 edges, delete 3 edges, then and then it will become a disconnected graph. So lambda of G2 is how much here? 3. So now let's write few notes on both lambda of G as well as the K of G. Okay. Theorems. Notes are nothing but the theorems are these. The edge connectivity of a connected graph G cannot exceed the minimum degree of G. That is, lambda of G is less equal delta of G, where delta of G denotes the smallest degree in a graph G. delta of G is the smallest degree. So here edge connectivity cannot exceed the minimum degree of G. Second, let G be a connected graph. G be a connected graph with n vertices. And E edges. Then lambda of G less equal the integer part of 2e upon n, where this denotes greatest integer part, denotes the greatest integer not greater than x. Not greater than x. Then the next one is that the vertex connectivity. The vertex connectivity of a graph G is always less than or equal to the edge connectivity of G. So that is K of G is always less equal lambda of G, right? Then one note from all these, the vertex connectivity of a graph does not exceed the edge connectivity and edge connectivity does not exceed the minimum degree of G. Therefore, K of G less equal lambda of G less equal delta of G, and the whole one will be less equal what? To greatest integer part of 2e upon n. E is the number of edges and n are the vertices, number of vertices. Okay. Then few examples let we solve. This is an example. Find all bridges and cut vertices of the following graph. This graph is given to us, suppose. Now the solution, the bridges are nothing but what? Isthmus. In a graph are what? Edges which does not belong to any circuit. Does not belongs to any circuit in a graph. Bridges are the edges does not belong to any circuit of a graph. So here, which edges doesn't belong to any circuit? Look at E5, then E8, E9, E10, right? E5, then E8, E9, E10, then E12, E13 are what? Bridges. Okay, now the cut vertices. The cut vertices in a graph are what? Vertices such that every path joining any two vertices such that every path joining any two vertices x and y in G passes through V. So here any path which should pass through that vertex. So here which are these? Look at this V2. Here some path will go through V2, right? So V2, then V3 also, then V4, V6, right? V6 should be like that, V10 and V11. V3, V4, V6, V10 and V11 are cut vertices. Okay. This is an example. Find edge connectivity and vertex connectivity of G1 and G2. G1, G2 are given here. So solution for G1, suppose in G1 this V7 is a cut vertex. V7 is a cut vertex. V7 is a cut vertex. So this gives K of G is what? 1. Smallest degree is 2. That is delta G is 2. Therefore, as K of G less equal lambda of G less equal delta of G, right, gives 1 less equal lambda of G less equal 2. Therefore, but G has no isthmus, no bridge, gives lambda of G is how much? 2. Lambda of G is 2. Then for G2, the minimum number of edges, whose removal disconnects the graph G2 is how much? 3, and the number of vertices required to disconnect the graph is also what? 3. Therefore, lambda of g equal to k of g equal to what? 3 here in G2. Next one. Question says that, is it possible to construct a graph on 7 vertices and 18 edges with edge connectivity 5? Justify. So let's check it. Solution. First of all, what is given? Given to us number of vertices, that is n equal to 7. Number of edges, that is e is equal to 18. And lambda of g is given to us, that is what? 5. Now let's find out this 2e upon n. So what does this? 2 into 18 upon 7. So this gives us 5.14. So here this is nothing but 5. As lambda of g is less equal 2e upon n, that is here 5 less equal 5. This is true. Therefore, yes, it is possible to construct such a graph. Okay. Now next question. Next example. Draw the graph for all these are what? 2. So the graph will be as such. Minimum degree should be 2 there. Edge connectivity should be 2. Means 2 edges should be deleted, then and then it will be a disconnected graph. And vertex connectivity is also 2. Okay. So this is a graph for this one. Solution for this. Suppose one more let me take. The vertex connectivity is 1. The edge connectivity and the minimum degree are 2. Suppose then the graph will be as such. This is a graph where vertex connectivity is 1. This is our cut vertex and edge connectivity is 2. If 2 edges are deleted, then and then this disconnected graph, and minimum degree is also what? 2. As such, the various examples on this one can be asked. So here we will stop for this video. Next video we will see an example on how to determine the shortest path using Dijkstra's algorithm. Thank you.